Good afternoon, everyone. I've decided against just completely removing 4.3 out of this course. I want to leave it as an option though for students if they want sort of a different look at asymptotes with rational functions. I think it's important if you're going to follow along with the course and try and get as much of the course outcomes as possible. And the other reason I made the decision, that first one, like I said, is that it is important, but also I know some of you went through asymptotes in advanced functions, and for a variety of reasons, that may or may not have went really well. So we're going to take another look at it here and just sort of work on some ideas here. This is going to be relatively quick though, okay? The content lessons follow the course, the video course here that I'm going to do here right away, and the textbook also does a really good analysis of it as well too. And we're going to talk a little bit about limits, and that's going to make it a little different. Okay, so what I want you to do for this first one is find the asymptotes of the function, of the given function here. And we're going to just try and sketch a graph here. Okay, so the first thing we always talk about is vertical asymptote. Okay, so vertical asymptote. Okay, just going to call vertical asymptote, right? A vertical line. Okay. I'm going to abbreviate this point from now on as VA. So the vertical asymptotes, or the VAs, exist when the denominator, okay, is equal to 0. Those are, okay, points of discontinuity or breaks in the graph. Now, this particular denominator is a quadratic, and we can factor it. It's nice when we can factor it. Okay. So we have two vertical asymptotes, okay, that exist at x equals -2, okay, and x equals 1. And on the graph, this is the first thing I do. I just put that dotted line all the way down. These two lines. Oh. Okay. So I would have my vertical asymptote at -2, my vertical asymptote at 1. Okay, and that's it. Okay, so if you're trying to graph it eventually, we could then look at horizontal asymptotes. Now, horizontal asymptotes, they are a little different. Horizontal, a horizontal asymptote, by its definition, is what's happening at the endpoints. Okay, so think of horizontal as the horizon. Okay, and as you look out over the horizon, you're sort of looking at endpoints here. Okay, so horizontal asymptote. Now, what we're looking at is always this. By definition, a horizontal asymptote is the limit as x approaches infinity of my function, and the limit as x approaches -infinity of my function. And really, I'm just putting in really, really large values here, okay, for x. Okay, now here's where we get into the limit idea and thinking about sort of some theory here. So if I put in really, really large values of x, really what I'm left with on my function, okay, if in a lot of ways taking away, okay, I've got a constant, okay, sort of value over x. Okay, so what I mean by that is what's happening as I put in really, really large numbers. Okay, does a -2 have any effect on a really large number? Taking away 2 from a large number? Not really. Okay, so we can sort of neglect that. Okay, x over top of x. Well, x over top of x sort of cancel each other out, and I'm really left with, okay, something like that. And I know this math isn't going to sit well with people, but that's what I want to talk about when I'm talking about sort of values of x way off in between. Okay, so way off in the horizon or at these, okay, extreme, okay, endpoints of a function here. And really, as we look at this function, we really go, okay, so what really remains here as I get really, really large? Well, I really have a number in the numerator divided by my variable. Okay? And that's really, in some ways, it looks like the denominator, just by virtue of this squared factor, grows a whole lot larger and bigger, okay, than the numerator. And the principle behind this is that if I have a numerator as a relatively small number compared to the denominator, which would be a relatively large number, right, just because of the squaring factor, okay, then I tend to find that I have the limit of my function as x approaches infinity tends to 0, okay, and the limit of my function as x approaches negative infinity tends to 0 as well, okay. But in this class, I'd like to go a little bit further, okay, and the fact that I have sort of a 1 over x thing, if I have positive infinity, it tends to 0 on the positive side or on the top of the function, and if x approaches negative infinity, it tends to 0 on the bottom. Okay, so this is what this looks like. I'm going to use this in red here to show this and change this. Okay, so out here I've got my function approaching 0 from the top. Okay, and over here I've got my function as x approaches negative infinity from the bottom of 0, from below 0, and that's represented with these plus sign and negative sign. I think we've talked about this in class. Okay, now what else happens? Okay, I should talk about the behavior at the endpoints, or sorry, the behavior of the function at my asymptote. So I've got, okay, just to classify this, that behavior, okay, near the asymptotes. And since I have two asymptotes, I want to define the behavior on both sides of the asymptotes. So the first one is as x approaches negative 2 from the left, and as x approaches negative 2 from the right. And then I've also got to find as x approaches 1 from the left, and limit as x approaches 1 from the right. Okay, now we do this in advanced functions, we do this in calculus, we can do this in a variety of ways. We can put in numbers into my function that are really, really, really close to, okay, really close to negative 2 on the left-hand side. So that would be like negative 2.001. Well, negative 2.001, if I want to do that, if I want to put in negative 1.99, okay, over here I'd put in something really close to 1 from the left-hand side, so like 0.99, and 1.001 on this side. Either way, I'm going to get, okay, this behavior. So I can put it in my original function, or I could put it in my sort of my working function here. But I want to be careful of the signs, right? I want to make sure I have the signs here. Either way you get this, it doesn't take you guys, I don't think, very long to realize that the resulting function, okay, is going to kind of look like this. Okay? And over here, okay, you might know this from advanced functions. And we also have this behavior and this behavior. Okay, so we're starting to fill in our functions just based on asymptote. I'd like to know what happens at 0. So what do I get when I have x equals 0? That might be another key point that I would check and try and find out here. So let's fill this in. I have, okay, so according to my function, I have negative infinity here. Okay, so this would be negative infinity. This would be positive infinity. Okay, this one would be negative infinity and positive infinity. And as I said, if you want to just try arbitrary values, okay, it could be like x equals negative 2.01, x equals negative 1.99. This one would be x equals 0.99, and this one would be x equals 1.01. Okay, we need to find one more point. What about f at 0? Okay, well, my original function, and I just want to find the behavior around the origin. I think it's, okay, in this area. I think I can probably fill in the rest. Right now I can't. So if x equals 0, what have I got? 0 over 0 plus 0, negative 2, 0 over negative 2, or 0. Okay, so I do have the origin as a point on my graph. I can fill that in and sort of have 10 through that. Now, I want you guys to always check these on Desmos and check, but that's basically sort of what we're looking at here with asymptotes. Okay, so what follows next is a couple of definitions of vertical asymptotes and horizontal asymptotes and what we kind of talked about here. So I'm just going to leave this up here for you guys. These are right out of the textbook, and we just worked through an example, so it should be relatively straightforward. We're going to go through some tricks though and tips to identify sort of horizontal asymptotes. And that last example had a horizontal asymptote at 0. Okay, and that was because the degree of the denominator was x. It was 2, and the degree of the numerator was 1. So the denominator grew larger than the numerator, so it tended to be 0. That was similar to this reciprocal function, and this is kind of what we had. Yes, we had some vertical asymptotes, but basically this reciprocal function looks like that. So I'll leave you guys to that and those definitions. We're going to work through another example here. But before we do that, we're going to talk about limits, and just a review of limits. And I want you to take a look at some of these. Okay, so let's take a look at this first one here. Okay, what would the limit, as x approaches infinity, of this example here? Okay, now look at the degrees. Okay, 2x and x. So we have a degree 1. We also should look at the constant terms. Okay, now let's use some sort of theory and logic here. Now, when I consider x to be infinity, or as x approaches infinity, I really don't have the -3 and the +1 really have no effect on the overall value of the function. So in a lot of ways, they're negligible. Okay, so the important part here is right here. Okay, now what's happening? Okay, as x approaches infinity, what's growing larger? Okay, I think the numerator, by virtue of this 2x, is growing double what the denominator is. Okay, so as numbers get really large, I can rule out my constants. Subtracting 3 or adding 1 to a really large number has no effect on the overall value. Okay, but what I do know based on my original function, is that the limit, should be 2, because 2 over 1, or 2 if you like, because the top, is double the bottom basically. Okay, and that's it. Now you may have learned this in advanced functions, where you look at the degree, and in this case, if the degrees are the same, so 1 and 1, right, then the horizontal asymptote is just the leading coefficients, and in that case it would be 2 over 1 here. Now with limits and with calculus, there's another way to do this, and you guys will start to see this here. Sometimes I can take out a factor of my term here. So where's my term here? Okay, and let's take an x out of the top and then the bottom here. So I would write that as, let me just, so if I took an x out of the top, I'd be left with, and if I took an x out of the bottom, I'd be left with, so my x's cancel. Now when I evaluate the limit as x approaches infinity, 3 over infinity is 0, right? And then 0, and really it's 2 over 1, So my limit can be expressed this way, and this is a technique that you'll maybe start to see get off to university and doing some math. Okay, what about the next one? What's happening here? Can we rule out the +1? Absolutely has no effect on the overall function. And what have I got here? Look at degrees and think about the function x over x squared. Well, as x gets really large, I'm tending to this situation, right? That I can approximate the function as 1 over x. So in a lot of ways, I know if I have negative infinity, my answer here is going to be 1 over negative infinity, or 0 from the bottom, if you like. That would be my horizontal asymptote, and that's Hey, you want to use our little strategy and trick from below here? Okay, like we did over here with this type of thing here. Let's take a look at this limit. Another way to see this. So my limit is x over x squared plus 1. If I factor out, okay, x from the, okay, so if you want to take out x squared, let's take out x squared, okay, or x, but let's take out x squared. Let's take out the highest degree, so the whole function, the biggest term is x squared, so I'm going to factor out x squared, okay, from the numerator. So if I factor out an x squared, okay, I'm left with 1 over x, okay, and if I factor out an x squared, I'm left with 1 plus 1 over x squared. Okay, does that make sense? Okay, now I cancel, okay, and evaluate. Okay, so now I've got, okay, can I put 1 over x over 1 plus, okay, now can I plug this in? What happens when I plug it in? Okay, so I've got, okay, 1 over negative infinity divided by 1 plus 1 over negative infinity, but that's squared, okay? So this is, okay, it's silly, I know, it's kind of silly. This will be 0, so I've got, okay, 1 over negative infinity over 1, or 1 over negative infinity, which we had sort of up here. Okay, next one. Okay, we've got a situation where as I'm trying to evaluate a limit as x approaches infinity, positive infinity, and I can look at the leading coefficients, okay, the terms, the biggest term or the degree of the polynomial, okay, is 2, the plus 3 and the plus 4 cancel each other out, okay, or they're negligible, and they don't cancel each other out, but they're negligible in my function, and even taking away an x really isn't negligible. So really this limit as x approaches infinity, and this only works when we're evaluating the limit at infinity or negative. Okay, so I have this. Okay. Okay. So my horizontal asymptote in this case, okay, is 2/3, and I could have gotten that from, okay, my leading coefficients, and the fact that, okay, the leading coefficients are my horizontal asymptote only when the degree of the polynomials are the same. Okay, that's a little different. That's a little different approach here with how to handle and evaluate limits. And if you continue with this in university, you'll even learn a different way to evaluating limits, okay, using derivatives, and that's kind of a neat thing, but I'll leave that for your university careers and your university professor. Okay, so horizontal asymptotes. What do we need to know about horizontal asymptotes? Okay, well, horizontal asymptotes approach a line, okay, a flat horizontal line, and we're going to call this L. Okay, so horizontal asymptotes may be crossed. Okay, a function can cross a horizontal asymptote. Okay, and it can be touched by the function can touch a horizontal asymptote. Okay, we're not too interested in horizontal asymptotes around the origin. We're interested in horizontal asymptotes, okay, at endpoints here, at the endpoints. Okay. Okay, so horizontal asymptotes can have there could be 2 horizontal asymptotes on any function. Okay, so this example here, I don't know what necessarily the equation would be, but we have a horizontal asymptote. Okay, y equals, and horizontal asymptotes are always y equals, right, expressed as y equals. Okay, and that's as x approaches negative infinity. And over here we have a horizontal asymptote by glancing at the graph at y equals 2. Okay, and that as x approaches positive infinity. Okay. Yeah, so oblique asymptotes are a little different here. Oblique asymptotes, okay, only occurs when the degree of the numerator is exactly 1 greater, okay, than the degree of the denominator. So here's an example of a degree of the numerator, 2, right, being 1 index higher than the degree of the denominator. In this case, it's 1 here. So 2 and 1 here, we've got that situation. Okay, and we've, okay, have to work through finding this oblique asymptote here. So I'm just going to clean this up a little bit, the little mark I made on here. Okay, and work through that. But this question asks for, okay, the question asks for all asymptotes. Okay, so let's start with the easy one, vertical asymptote. We've got a vertical asymptote, okay, when our denominator is equal to 0. Okay, so we have a vertical asymptote, okay, x plus 1 equals 0, okay, or x equals negative 1. Okay, we've got a horizontal asymptote. Okay, let's look at our function. So we're trying to find the limit as x approaches infinity of my function, the limit as x approaches, and the limit as x approaches negative infinity of my function as well. Okay, so what do we have here? Well, what's happening? You want to do, okay, you want to start looking at, okay, situations here. What happens when x is a really, really large number? What sort of tends out here? Well, it looks to me like, okay, that those are probably negligible. The 3x and the 3 are negligible. They don't have a whole lot of value. The biggest thing right here, okay, is that. But keep in mind that, okay, I should have maybe talked a little bit about, okay, before I went that way. I should have maybe talked a little bit about this, okay? So if I get rid of my, okay, and then think about this as I'm dividing by, remember that technique I did before? Okay, let's divide everything by 2x squared. Okay, so if I take an x squared, okay, so I'd have 2, I'd have 3 over x, and I'd have a minus 1 over x squared. And then I would also have then divided by, okay, so I'd have an x squared, and I'd have 1 over x, and I'd have a plus 1 over x squared. Okay, so what have I got here, and what am I left with? Okay, so I've got a situation where, okay, these are all, okay, 0 here, okay, and I'm left with, okay, really like a 2, okay, a factor of 2x here. Okay. So really, okay, that's kind of what I'm left with. Okay, the 2x squared over x leaves me with a 2x, and as x approaches infinity or negative infinity, I'm really tending to, okay, so I don't have, there's no horizontal asymptote here. Okay, so I'm tending to go off here. Now, if there's no horizontal asymptote, you should consider oblique asymptote. There are the occurrence of an oblique asymptote. And in this particular case, okay, I have a situation where the degree is 2, the degree is 1, it's 1 higher. So we're going to just do, okay, long division here really quickly, okay, and figure out what this oblique asymptote, and we're going to see, okay, this little result occur again here, and sort of talk a little bit about that and explain that. Okay, so let's look for our oblique asymptote, and this is how we find an oblique asymptote. Now, I like to do long division. Okay, if you guys want to do synthetic division, by all means be my guest. Okay, so I need to multiply by 2x, and when I multiply by 2x and x plus times x plus 1, okay, I'm going to get 2x squared, and 2x times 1 is plus 2x. Then I subtract. Okay, so I subtract and those cancel, and then I subtract 3x, take away 2x, I've got an x, and I can bring down my minus 1, and that's as far as I can go. That's my remainder. There's no way through multiplication I can get x plus 1 to become x minus 1. So that was simple. That's, okay, bang, right there. Okay, I could, okay, maybe do like this. Okay, I guess to finish it off, but I'm getting close to finishing. Okay, so that would be a plus 1, and that simplifies. Yeah, I guess I should have did this. I didn't have my remainder first. Okay, I should have just did this extra multiplied by plus 1. So now I subtract, and my x's disappear, and I've got a negative 2 as my final answer here. So what I'm going to do next is just to try and show this here. Okay, so what's happened here? Here's my original question. my division statement, okay, I can be, that original polynomial can be found by multiplying my x plus 1 and my 2x plus 1, and then take away my remainder. Okay, so that, if I did expand that out, this is called a division statement, and we used to do this, okay, way back. Okay, so that's how I found it. This was my whole number here. I found it by multiplying my two, okay, my divisor and my dividend here, and then adding my remainder here. But this original polynomial is really close to my function. What was my function? Okay, my function was 2x squared plus 3x minus 1 divided by x plus 1. Okay, so how close was that? Here's my original function. My original okay, quotient here was, and to get that to my original function, I divided by x plus 1. Okay, so what happened here? Okay, so this is going to cancel, but I have to carry that into here. So my original function, the way it was given to me in the question, was like this, but through division, I've written it like this: 2x plus 1, take away 2, divided by x plus 1. Okay, and this is in fact a good way to see this function. Okay, so my function, although I was given it to it like this, I actually performed the division and I rewrote it like this. And this is kind of what Desmos graphs here. I'm going to end the lesson with calling this function up in Desmos. Okay, so when it's in this form, we get to easily see the oblique asymptote. Okay, this is the oblique asymptote right here. Okay, and this is the sort of the endpoint, okay, behavior. So it falls along the oblique asymptote. Okay, it turned up here. Okay, so that's my oblique asymptote, and that's a straight line. So the function at its endpoints tends to this straight line. Okay, and then this in here, okay, is sort of my, okay, a combination of what's sort of happening around the origin. Okay, we can see occurrences of the vertical asymptote here. Okay, we can see a sort of a reciprocal function, right? So I'm going to pause this, okay, and call up Desmos and finish the lesson here, and that'll be long enough for this one here. So I'll be back in a second. Okay, so here's my function graph in Desmos, and we get to see that we see the vertical asymptote. If I zoom in, okay, we see the vertical asymptote at -1. Okay, we see we don't have horizontal asymptotes, but we have oblique asymptotes. And I'm going to zoom out, okay, and I graph this oblique asymptote here as well too. So if I see endpoints, it just tends really close to, okay, that function just gets closer and closer, and even over here, okay, I see the end of that blue function and graph. Okay, and the red, our original rational function, approaches that endpoint here. So that's what it looks like in Desmos. For all of these questions, if you're going to try any of these, I want you to always be graphing them in Desmos and seeing what they look like. And good luck with the questions, and play around with them. Thanks. Have a good one. Bye.